Okay, hello grade 11s. How is everybody doing? Okay. Hopefully mic is on. Let me button up here. Is everyone doing okay? Had a good weekend? Productive? Had some fun maybe? Enjoyed the cold weather out there? Mic is on. Okay, I think we're good to go. Alright, so, this week is gonna be our last. Kind of sad, huh? This will be the last week of class, so to speak. So this week we'll be looking a little bit into magnetic fields, how it works with currents. Kyle, hello. How it works with forces, and we're gonna talk about current, magnetic fields, and forces. Specifically, the short of it is that we're gonna be looking at right-hand rule. We'll talk a little bit more about what that is. Let's just quickly, I guess, have a look at our week to come. Let's have a look at that first. Okay, so today and tomorrow we're gonna have 2 lessons back to back. There will be one worksheet. I'll post it today, but it requires you to know a little bit about tomorrow's lesson as well. I'll post some stuff tonight, some worksheet, and we'll take that up on the Wednesday. Miss Farag and we have just finished the electricity assignment. I'm reading her text right now. Yep. Okay, so we're good to go. She's proofread it. So I'm actually, you know what? Let's do that right now. So Miss Farag could also do this in her own classroom. She'll do it soon enough. We're gonna post the electricity assignment for the assessment. Sorry. Same as we've seen before. A Google Forms, a knowledge section, a thinking section, and an application section. It's gonna be a lot shorter. It should take about half an hour to complete. So maybe I'll just create that right now. Material. E and M assessment. It's a pretty short one. It will only cover up to, well, Tuesday, tomorrow's lesson. So if you want to wait till tomorrow's lesson to do it, yeah, no biggie. But I'll put it up now. You know what? I shouldn't waste time here. I'll do it later. I also put material anyway. Yeah, whatever. Okay, so today we're going to be looking at magnetic fields and what's called Oersted's principle. I guess we'll just jump into it. There was a question here. Could you take up question 2 from the combination circuit worksheet? I took it up. It was done on stream. But if you're not satisfied with that, head on to our circuit section, and I uploaded the completed notes, and I do want to make a note. Okay. I think I have to download it. It won't show the. Let's see if we save link content as. Nope. Okay, we're gonna do it the long way. Open with. No. Why is it being like that? Okay. Let's see here. Open a new tab. That's what I wanted. Then we have the option. I don't know why the option to download isn't always just like right there. So just one quick note. I forgot who sent me an email. I think it was Caleb Ang. And he noticed that I've made a mistake somewhere, in a truly rare occurrence. I want to go over that real quick. Was it in here? No, it wasn't here. What am I doing? It was from this worksheet. Let me just pull that out. The extra, yep, okay, this is the one I was looking for. Whatever. Yeah, actually, let's do this one instead. Yeah. New tab. I'm just curious. In your other courses, do you guys have culminatings, or how's that working out? All right, let's open this up. Okay, and I was so proud of that solution because, I really took my time with it, and I thought I organized it really well. Yeah, here. It was, I think, right at this step. Right at this step here. So, math culminating was optional. Cool. Okay, it was at this step here. Thanks, Z. I think it was R2 to 7. R2 to 7. So, 2 to 7 was where is 2 to 7? No, 2, 5, and 7 was this chunk. Where is that chunk? 2, 5, and 7. Here. So 2 to 5 and then 7. This was series. However, 2, 5, and 7, that orange part and this resistor 6, they're in parallel with each other. So I made a mistake here. I should have used parallel rules, but by accident, and big brain here, I just added them up like they were series. But see, look at resistor 6. Resistor 6 over here is out here. Resistor 2 to 5 and also 7 are parallel to that. So I should have used parallel rules. However, if you look at the solutions that were also posted over here, no, not that one. Over here. This solution is correct. 5.76 ohms. I did this one a lot better. Go figure. Okay, so that's that. The final answer was off, but the steps are okay. Just accept that parallel one. I should have used parallel instead of series. Okay, we're going to jump into today's lesson. We're talking about magnetic fields and Oersted's principle. So I guess a little bit of maybe recap here. I don't know how much you may have been taught maybe in grade 9 and 10 about what magnetic fields are. Oh, okay. So what is a magnetic field? A magnetic field is the distribution of a magnetic force in the region of a magnet. And also extends around the magnet. So essentially, think about like a magnetic field similar to what a gravitational field is. What's both? Maybe you might be saying. Okay, well, if we have, let's say this is the Earth, right? If we draw maybe concentric circles around it, we can talk about, okay, the force of gravity when we're this far away from Earth is like 10 newtons. The force of gravity on an object this far away is 5 newtons. And the further away you go out, the weaker and weaker it gets. That's a gravitational field, where it talks about the influence of gravity depending on where you are relative to the Earth. Similarly, when we have magnets, they do create magnetic field lines, where they talk about, okay, if we have a random magnet, let's say even a bar magnet, north-south, there's some sort of influence that exists around this magnet that will attract other things that could be magnetic or other magnets themselves. So like things like iron, you've seen it. Like if you have a magnet, you stick it on your fridge. The reason why it sticks to your fridge is because it has some sort of influence on the metal that your fridge is made out of that allows it to be attracted to it. And it also works the same for repelling. There has to be something about these fields that cause them to be pulled together and pushed apart. But unlike gravity, it is able to do both. Gravity only acts in one direction, only attractive. Okay, so the way we describe them is what we call magnetic field lines. And maybe you've seen this before. I thought I pulled up some photos, but I guess I didn't. Let's just pull up some photos. If you look at magnetic field lines. Oh, there's a really good animation I saw earlier today. Magnetic fields. I think this one's good. I saw one that was really good. Anyways, so the magnetic field lines are kind of what we see. Like if you toss on like iron filings on a magnet, they create this nice, cute little pattern. Essentially, what's happening is that the metal shavings on this part over here, so the little iron shavings, they're like splinters. They're kind of longish, and they align themselves in such a way that they want to point in a certain direction. That's what a magnetic field line is. It's just the ways that the magnetic flux fills our space. And another way to think about it is that if we were to put a compass with a compass, this is what I was looking for. That's a decent photo. Let's have a look. Too bad you can't get bigger. Essentially what it is that if we're at a certain magnetic field line, it will tell us which way is north. Obviously, that also works for the Earth, too. Because, well, near the Earth, wherever we are, if you have a little compass, it'll point along a magnetic field line pointing towards the north. Obviously, like it's a little bit different further out you go, or like depending on where you are on Earth. Earth's magnetic field changes a little bit, things like that. Okay, so I think that's sufficient to describe magnetic field lines. Where are we at? Over here. So, those are magnetic field lines, and sometimes they're called the north-seeking pole. What does that mean? If we were to draw a compass and we were to slap it in there, we just drew a compass. Essentially, they would point in the direction of north, the north-seeking pole. So we put a compass over here, and it will align itself to point in the direction of north. Let's describe a few things. Magnets versus non-magnets. As we saw, magnets can attract other magnets. Opposite poles attract. So north attracts the south. Another thing. Actually, no, we're getting into that later. What about a magnet and an object that isn't a magnet? So there are some types of metals that are able to be attracted to metals and some that are not. The ones that are able to be attractive are called ferromagnets. So, like the name suggests, the main one that is attracted to magnets or can be magnetized easily is iron. But also nickel. There are a couple other ones. I can't remember off the top of my head. Anyways, so what is a magnet? How do we get magnets? Do they just grow out of the earth? Well, kind of. The way that we think magnets come about is what we call domain theory. Magnets are all made up of smaller magnets. So, and rotatable magnets called dipoles. Ooh. If you took chemistry, you definitely know what a dipole is, but don't worry, we'll talk about what it means in a physics standpoint as well. Which can interact with other dipoles that are close by. If all the dipoles line up, then you are going to be able to produce a magnetic field. A small magnet domain is produced. Okay, so what are they talking about? First of all, what's a dipole? A dipole is anything that has a difference between its two ends. So let's say if we're talking about a battery can be considered a dipole because it has two poles. Di meaning two, poles meaning ends. Two ends. So they're different ends. So if we have a battery, it's a dipole because we have a positive terminal and a negative terminal. For a magnet, well, it's a dipole as well because it has a north terminal and a south terminal. Every single magnet has one. Now, sometimes they're drawn as arrows. So these ones over here are different kind of directions of our domain. You may not think about it. Like we think of when you say the word crystal, you might be thinking about okay, like things like maybe glass, sapphires, diamonds, other like gem-like structures. But guess what? Even metals have crystal-like structures. I don't know what is a good example of talking about it, but metals have grains and crystals as well. So when a metal is heated up and then like cooled down, the way that it like when it resolidifies, the certain crystals line up in certain ways. So you can actually manipulate that to make it magnetic or non-magnetic. We'll talk about that a little bit later on. Anyways, so if you have a material where its dipoles are pointing in every which direction, well, they're all random. If they're random, well, then there's no producible effect that can be seen outside of it. If the magnetic field domains are, if a magnetic field and a magnetic material, the domains are not lined up, essentially what we're saying is that inside the crystal-like structure of this metal, there do exist regions where the metals can point in a certain direction. But here, these ones are rotatable magnets, whereas these ones are not rotatable, maybe they're fixed. So in a magnetic material, they will have domains that do exist, but they don't have any net direction. In a magnet, there's clearly a north-south thing going on here, where you can see in these ones, maybe there's a north-south business here, but maybe that's different from this north-south domain on this side. The more aligned the domains are, so if each of these patches are pointing in generally the same direction, the more like a magnet it will behave. This is the reason why if you take a nail and you wipe it, if you rub it against the magnet over and over again, what you're doing is that you're forcing these little domains to start to line up so it fits the magnet. A magnet will always have its magnetism unless it's disturbed, smashed, melted, blah blah blah. But something that is just magnetic, like an iron filing or a nail, something like that, you can make it magnetic by influencing those domains to start to line up. So what's a magnet? A magnet is a thing that has lined up domains, which produce a north-south effect. This one over here, they have norths and souths, but they're all random. So there's no influence, or it doesn't create a magnetic field that does anything. Okay. I do want to take some questions in case some of the concepts here were a little funky. No way. Okay. You meant in the other question sheet. Maybe if you have time today. Our lesson's not too long. Okay. Okay. Magnetic properties. So we have some definitions here. Magnetic induction. We magnetize a ferromagnetic object by encountering a strong magnetic field. So the example I gave of taking, you can make something magnetic. Like you make a iron nail, iron nail magnetic by rubbing against a magnet. You don't actually have to rub it. You just have to bring it really close to a strong magnet. But normally the magnets we try to do with are kind of weak, so we actually literally have to make contact. If you have a strong enough magnet, well, it doesn't matter. Actually, if you have a strong enough magnet, you don't even have to make contact. It will be able to restructure the ferromagnetic material, that nail in this example, and make that nail into a magnet. In fact, we've seen that as well. If you've ever grabbed a magnet and you attached it to a paperclip, and now that paperclip was picking up other paperclips, this is a good example of magnetic induction, because the one magnet is making the other metals into magnets themselves. So you're inducing magnetism on the other objects. Demagnetization is when you lose the strength. This is done by, well, either you leave the, let's say if we're talking about those paper clips, if you leave them away from the magnet for a long enough period of time, eventually because we know from kinetic theory, those atoms are, wiggling and jiggling about. Those domains don't want to stay aligned for long. Eventually random motion will cause them to, deviate. Reverse magnetization, this is very difficult. When you reverse the poles of an object without using electrical current. I'm going to skip this one. Maximum strength is when all the domains are aligned. So something like this here is a very strong magnet because all the domains are literally pointing in the same direction. You can still have a magnet that, is not as strong. So this example there was with a neodymium magnet. Maybe if you had another magnet where, I don't know, they're all pointing, let's say, up, but, some are like this, some are, somewhat upwards. It's kind of like that, maybe. Where they're still generally pointing upwards, but, their directions are still kind of conflicting with each other. Okay, if you broke a bar magnet in half to split the north and south, what would the outcome be? Well, because of domain theory, if we have a magnet north-south, it's not saying that this half of the magnet is north and this half is south. No, the bar magnet is literally just domains, right? And in those domains, they're all just pointing in the same direction. They're pointing north. So if you were to cut it in half, guess what? You would get two bar magnets with the same direction it originally had because the domains were all lined up. Okay, so magnetic field and compass. You have a look. So like I was saying before, a magnetic field will determine what a compass needle will point to. A compass needle is also a small magnet, but not like, I guess it's normally influenced by other magnetic fields around it because it's something more stronger than it. So it will line up to match the magnetic field of whatever we're talking about. Okay. I think we're going to get into magnetic field lines next. How to draw magnetic field lines. Okay. A couple of rules. So we generate the field lines from the north. We know that inside a magnet, the domains point. We're north seeking. We're north seeking inside the magnet. So when we draw magnetic field lines, we draw them in such a way that they go from the north pole to the south pole. The arrow points from the north to the south. It's generated from the north and goes to the south. That is the way we kind of draw them. So if we were to do the magnetic field lines here, we will see what happens, let's say. You know what? Let's do one in between. Let's just draw the magnetic field lines for just one magnet alone. Let's say we have a neodymium magnet. Those little coin magnets. They're really strong, and you use them for fridges. You can use it for other things. If you ever have like something that like a door that opens and shuts, but it has a magnet that kind of like normally little small windows or doors have those little magnets to close and open them. They sometimes use neodymium magnets. Let's say we knew that in our neodymium magnet, the top part was the North Pole, and the bottom half of this magnet was the South Pole. What would the magnetic field lines look like? We generate or start drawing our magnetic field lines from the North Pole. So we draw them from the north, and they seek out the north again by passing through the South Pole. So we draw the arrows coming out of the north, pointing towards the south. Out of the north, pointing towards the south. And obviously this is 3D, because we're talking about a coin here. As I said that, I just kind of messed that up. We draw magnetic field lines coming from the north and going towards the south. Now, before we get to these ones over here, I want to do a couple examples. Well, one example. What if we have, what do magnetic field lines look like if we put them beside two magnets? Maybe we'll get to see something. Okay, so pens. Let's do it in the same colors. We have north as red, and we'll put the other north pole here as well, north. And then we'll do blue for south. 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 Okay. All right. So let's draw the magnetic field lines for both of these. Okay. So like we said, it comes from the north, goes to the south. From the north, goes to the south. And you know what? Because, well, they're two magnets, well, there's no reason why this couldn't happen as well. The other rule for when we draw magnetic field lines is that we can never cross lines. A line coming out of here would not be able to cross through and go something like that. We can't do that. We can't cross lines. Right. Okay. Now, what would the magnetic field lines go here? Well, there would be some magnetic field lines that go from here and wrap around. But guess what? There might be a closer south pole over here. So some of the magnetic field lines will point straight at it. And when we get these magnetic field lines that all point in the same direction, we get attraction. So when opposite poles of a magnet are close to each other, they're attracted to each other because their field lines are aligned. They aren't fighting each other, they kind of flow together. So this is what it would look like. All right, not bad. Okay, maybe you might want to see what would the field lines look like if they were opposites, or the same poles that were. Okay, delete. Let's do south to south, south to south. Okay, what happens here? Let's go with red for the North Pole, and red for the North Pole, and once again green for the lines. Okay, we want to do a north to south here. We also want to do a north to south. I can't draw the north to here. If I try to do that, well, let's see what happens. Then I would get these ones over here, and whoa, wait a second. I would be starting crossing lines. This is not allowed. So it turns out here, the magnetic field lines are kind of competing for space, where we see clearly that there would be a line where the magnetic field lines would not be able to cross each other. Let's just get some examples of these from the web, because that might be a better way of depicting them. Magnetic field lines, magnetic field bar magnets. Okay, let's have a look. Sure. So when we have two bar magnets that have opposite poles near each other, we clearly see that there is a direct. We can connect the field lines from one to the other without crossing anything over. However, if we were to flip them around, we see that the poles are sort of in competition with each other because we can't cross those lines. You know what? Let's get a bigger picture here. And there was a question. I'm going to have a look at that in a second. Okay, that's not a bigger picture. Anyways, so we can clearly see when we have two of the same poles try to push each other. And that's why, well, you can't put two of the same poles together because they repel each other. Those magnetic field lines are fighting each other because, well, they can't cross. The opposite is true. When we have two opposite poles, they want to attract each other because they literally go, the magnetic field lines go from one magnet to the other, the north of the first to the south of the second, or whatever, vice versa. There was a question. Why do dipoles need to line up to be magnets? They don't need to perfectly line up to be magnets, but why do they need to line up? Think of them as little, I don't know. Well, actually, this is perfect. We've done vectors. Thank you. Like, it's been so long since we even talked about vectors, right? They're vectors. You know what? Let's just consider a simple case. So I like this question. I want to get into it a little bit. Let's say we had some material. We don't know what. And I'm just going to draw the dipoles. We'll draw 1, 2, 3, 4, 5, 6, 7 right arrows, and I'm going to draw maybe 3 left arrows. 1, 2, 3. So what's the overall if we add all of them up? Well, that's equal to, well, maybe we cancel out some pairs. So this pair cancels out, this pair cancels out, this pair cancels out. So in the case where I drew some arrows pointing left, some arrows pointing right, well, some of them will cancel out. You can think of them as vectors, one going 1 meter left and 1 meter right. Well, those ones will cancel out. The overall, or like charges, we have 7 positive charges and 3 negative charges. We're still left with 4 positive charges. And now this is strong enough to create a magnet. Now, they don't need to perfectly cancel out. The more aligned they are, the stronger the magnet. The less aligned they are, the weaker the magnet. I guess everything can have some magnetic kind of properties to it, but normally most materials are very weak because the domains are random. So let's say we had a random one, maybe 1, 2, 3, 4, and let's say we have still the same 3 left arrows here, 1, 2, 3, and in the end we would get a net domain dipole of just 1 here. This one had 4, so it would have a stronger magnetic field than this one. This one still would have a magnetic field, but it'd be really weak. Good question. Okay, draw the magnetic fields for these ones. You know what? Let's give some people time. Try it out on a piece of paper. 3 minutes, 2 minutes, 3 minutes, 2 or 3 minutes. We'll take it up. So start them from the North Pole. Draw your lines to go to the South Pole. See how it happens. See how it works. Good luck. And don't cross lines. All right. Hopefully that was enough time to kind of get a feel for how things would go. Let's give it a shot. Okay, so let's say we start off with the left diagram over here. Maybe we start off with the top magnet. The top magnet, okay, on top, well, there's no influence of the magnets around, so yeah, easy, north to south. Not bad there. Now here in the bottom, we might want to be careful. Maybe we'll say that this south pole is a little bit closer, so some of the field lines will come from here to here. Cool. Could some of the magnetic field lines pass through here? Sure. Yeah, you would get that as well. What else? This magnetic field line would go from here to here, perhaps. You would definitely also get magnetic field lines going from here to here. And once again, because we see like of these lining up, the kind of the gelling of these magnetic field lines, none of them are opposed to each other. We would get an attractive force. Well, kind of predictably. The north would attract the south, and the south would attract the north. These things would go... Oh, I shouldn't draw those arrows. There would be attraction here. Attraction. Okay, let's have a look at the field lines here. Maybe we might want to start with some of the field lines. Remember, always start with the North Pole here. The North Pole would create field lines that look something like this. Alright, wonderful. So we will get something like that. Some of the north ones would come out here. Boom. Not so bad. You could technically also do some of the field lines like these. I kind of avoid those. I like to draw just them from the poles, but you know, those still exist. You would get some field lines here. We will get stuff like that. So anyways, we see that there would be attraction here between these two, but there would be repulsion here, because look at the lines here from the edges. If I were to draw the lines here as well, we see that these lines are being compressed. They can't overlap each other, but because those lines are so close to each other, they're going to repel from each other. versus these ones here, they all kind of go in the same direction. Okay. Let's have a look. The next thing we're going to cover is what's called Oersted's principle. I think there's supposed to be like a, I don't know what that's called in language when it has like the two. I don't know. Remember if it's on the O and the E. Whatever. Oersted's principle. The idea is that, well, it's weird. We just went from talking about electrical components, and now we're talking about magnets. What's the connection? Well, it turns out we like to talk about electricity and magnetism together because, well, they're closely related. And the rest of today's lesson and tomorrow's lesson will be talking about how they relate to each other. Okay. What are electromagnets? So we're going to talk about electromagnets. We're going to talk about how to create magnetic fields using movement of electrons. So let's have a read. Oersted's principle is a charge moving through a conductor produces a circular magnetic field around the conductor. Whoa. Okay. So not only does when electron flow through a circuit, it's able to transfer electrical energy to the different components of that circuit, but as it does so, it creates a magnetic field around the wire or around the way it travels. Kind of weird. If we have an electron just traveling this way, it's going to generate it's going to create a magnetic field, those field lines this way. And today and tomorrow, the rest of today and tomorrow as well, we're going to be talking about how to determine the direction of, there are three main things. ILB. F. So we'll talk about current. We'll talk about magnetic field. And force. So today, the rest of today and tomorrow, we're going to be talking about how, if we know two of them, let's say the current and magnetic field, we should be able to figure out what the direction of the force is. If we know the force on something and its magnetic field, we should be able to determine what direction the current is. That's the rest of, yeah. All right. So we talked a little bit about before in grade 9. We talked about conventional flow and electron flow. This is why we kind of stuck to conventional flow, because when physicists were working with the conventional flow, they determined all their laws around that. Now, there's another way to go about electron flow as well. We're going to go through both of them. All right. Imagine being a chemist. This slide was brought to you by the Physics Can. That's an old slide. Anyways, so today is going to be all about, the rest of today and tomorrow is going to be all about how to use our right hand. Hopefully that comes off as my right hand. Whatever. Using your right hand, this is my right hand, by the way, how we can use that to determine those three things I was talking about. Namely, we're talking about force, magnetic field, and current. Each one of these has something to do with magnetic field, current, and force, motion, sure. That's the rest of today and tomorrow. Okay, so we call it the right-hand rule. So when we talk about a circuit, in order to figure out how a moving charge creates a magnetic field, first of all, we want to work with, when we're doing the right-hand rule, we work with the conventional flow. Conventional current flow. Current flow, we're talking about conventional here. So I'll put a little star. We're talking about conventional. Okay, if you want to do electron flow, you will have to use what's called the left-hand rule. Here's how it goes. If we know the way that the conventional flow is through a wire, we point our thumb in the direction of the current. If our thumb is the direction of the current, then our fingers are the magnetic field. So in this example here, if the current is, well, for conventional current, positive terminal to negative terminal, the current is this way. The magnetic field on the wire goes below the wire. Let's say below the wire first, goes into the page, and then around the wire, and then out of the page when it's above it. So if let me get an object, I suppose. Let's go here. Do I have something? Whatever. I'll improvise. Okay, I'll use a pen. So I got my highlighter over here. Let's say the current is traveling to your... The current is going this way, in the direction of my thumb. Then my hand becomes my fingers of my hand, my fingies become the magnetic field. So if I put my thumb in the direction of the wire, it tells me that below the wire, well, the current is going for me towards you, and then as it comes, well, towards you, behind it, it comes... essentially what I'm saying is that the magnetic field goes something like this. It creates a circular magnetic field around the wire. The right-hand rule is the rule we use to determine those directions. Thumb points in the direction of the current. Our fingers, as we wrap around, will generate that circular magnetic field around the wire. That's what this picture is trying to get across. Okay, the thumb points in the direction of the current, and then our fingers are the magnetic field that's generated. That's what these blue lines here are. They represent the magnetic fields. Obviously, it would be a little bit different here. The magnetic field generated would be something like this. The magnetic field. So another thing to remember here is, I guess, the magnetic field is going to be 90 degrees to the direction of the current flow, and also 90 degrees to the force. Okay. Like I said, you could also use, if you're working with electron flow, we want to use the left-hand rule. So it still does the same thing, and it results in the same circle, by the way. It's just okay, so if I use my right-hand rule, this is the magnetic field I get. Well, if I want to get the same magnetic field, I have to use my left hand to point in the electron flow, and that gives me the same magnetic field. They both go, I don't know, for me it's towards you, below the wire, and as it comes above the wire, towards me. Okay. So, how do we determine if something is going... Because these are 3D objects, the way we're talking about magnetic fields going in and out, the convention we use is... if we see something that has a circle with an X in it, that means that it is going into the page or into something. If you see a circle with a dot in it, so this one, let's just redraw it. This one over here is into the page. You'll see it like this. That means into the page. It shouldn't say current. It should say into the page. It could be current. It could be something else. And this also means just out of the page. So specifically, if it's a current, if you're telling us if we have a current going into, let's say, the camera. If it's going into the camera, we get a clockwise magnetic field. If it's pointing towards me, coming out of the page, I'm getting a counterclockwise, or yeah, CCW, magnetic field as it's pointing towards me. The reason why we need the dot and the cross is because to tell us into and out of the page. You might be saying, Mr. D, that's hard to remember. Maybe. The best memory technique I have to remember, X is into the page, dot is out of the page, you may have your own, is something like this. Imagine you're shooting an arrow, okay? You draw your arrow back and you let go. Now, you're not just shooting any arrow, you're shooting this weird fancy arrow. The tip of the arrow is a cone. Looks something like this. Yeah, cool. It's a cone. And obviously you have the stem of your arrow, and at the back of the arrow you have feathers. And the feathers look something like this. Can I draw? Maybe. Okay. Not bad, not bad. Alright, it looks way better than I thought it would. And the feathers make a little cross, right? So imagine, what do you see? If I fire the arrow at you, you see the front end of that cone. All you see is maybe that. If it's coming straight at you, all you see is maybe the tip and then the circular shape of the cone. So it's coming towards you. That's the arrow coming towards you. You see a dot. If you are the one who shot the arrow, you see the back of the arrow, right? So you still see the circle part of the cone, and then the feathers make the X. That's the way I like to remember it. Okay, cool. So, practice here. If these are the magnetic fields, what is the current? So determine the current. Determine I. So 2 minutes. Give it a shot. What is the current in this one? In this wire? What is the current in this wire? What's the current in this wire? Good luck. So play around with your right hand. Try to get it to line up with the wire, and then see which direction your thumb points in. Same thing with for A, for B. You'll have to figure out which way makes the right type of circle around the wire. And for C, you got to determine, well, is it going towards you or into the page? Give that one a shot. And that's it for today. All right. Take some time, finish that up. Let me see here. Do we have any questions? What are domains? Domains are just the shorts. It's electrons. Domains are made up of electrons. Electrons, if you go on to take actually even grade 12 chemistry, they will talk about electron spin. You can have spin up electrons and spin down electrons. Depending on the type of spin an electron has, that will eventually determine the magnetic property of material. But what we want to think about domains as physicists, they're almost like tiny, the smallest bar magnets we can create. Regions where we have bar magnets pointing in certain directions. Okay, I think that's probably enough time. Let's go through them one by one. So for A, we can clearly see that if we talk about the magnetic field, here, it's going into the page. Can I hit 50 subs before school ends? I don't know. Oh, I also got exciting news, but I don't know when to share it. Whatever. Probably like last day of class, tomorrow. Tomorrow's like the last class. Quick reminder. I'm still gonna run interviews, conversations with people who want them. We'll do as well as our practice exam next week. It'll be the Monday and the Tuesday, maybe a little bit of Wednesday. Thursday, Friday will be more conversations if you want to talk about, if you have questions about your marks, stuff like that. We'll have some office hours for that. Anyways, so here we see the magnetic field is going into the page because it's going behind the wire. So it's going behind the wire. If I'm going from top to bottom, the bottom part is going behind the wire, so that is a X. And up here is a dot. You didn't have to do that, but if you want to imagine it, okay, so here's the wire. Your current is going in and then towards you at the top. So the way I need to put my right hand to that is like this. And now my just be careful, my camera is opposite of yours, so your perspective. So for me, this current is going to the right. If I put it in like that, you know what? Can I just fix that real quick? Maybe transform. Flip, vertical? Nope. Wonderful. Transform, flip, horizontal, and now flip vertical again. Transform, flip, vertical. Okay, is that better? Yeah, there we go. Okay, so here's the wire. It went into the page first and then out of the page. So the only way for my right hand to do that is if it points right. I can't make it go into the page at the bottom. Actually, even if you did your hand upside down, you would still get the same right answer. Into the page and out of the page, well, that's why we use right-hand rule. Okay, so the current should be going to the right on the first one. I is this way. Here, in order for us to create a magnetic field that, when the magnetic field between us and the wire is going up, and then behind the wire is going down, well, the current must be going to the left. Obviously, well, it has to be opposite for this one. Current is going to the left in this wire. In this wire here, in order to create those counterclockwise magnetic fields, so in order to get my fingers to wrap in the right direction, I need to have my thumb pointing at me. Pointing at me means I need a little dot to tell that the current is coming out of the page towards me. All right, that's it for today. There was a question about doing some practice question. I'm just going to point you to the solutions. Hopefully you can piece it out from there. So you said from the other worksheet, so combinations. So you were having trouble with this one over here. Well, I didn't put in all the steps here, but this is how you would do it. You would the first thing you need to do is combine these two as a series circuit, create one resistor. Then this R2 is parallel to R3 and R4. Then you would get the, what's it called? The total resistance of all three, and then of the last one. Once you get the total resistance, now we can find the current of the whole circuit. That's what we were missing before. So then you would get the total resistance, get your total current using Ohm's law. Once we have that, then determine, do the circuit analysis part of, okay, which part gets all the current, where does the current split up, okay, how much voltage does that take? You have to go through that step by step. Okay, I am going to sign off. Okay, cool. All right, cheers, everybody. See you tomorrow. Last lesson for grade 11 physics. Wow, exciting. All right, take care, everyone.